buck converters last time. So we had a small 5 amp one, then we had a bigger 5 amp one. We had a same size 10 amp one, but the internals were definitely different versus the 5 amp one, because this at 6 amp got a whole lot hotter than this one at 10 amp. And then we have this beefy boy 5 volt 15 amp here, which almost didn't register any heat at all. So we have different sizes here, and well, so today, what we're going to do today, we have, I should have multiple of these. Yeah, so I have 3 bags here of ws2812 strips, right? So let's get those out of the bag. We have these 3 strips, right? So, what direction are they? Okay, so they go from the outside. And we have a 24 volt power supply. This should be, yep, UHP24. Not sure you can see that, but it's the 24 volt version, so that's good. Let me plug that in real quick, but the socket is still turned off. Okay. And okay, let's start with wiring up the QuinLED, and then we'll continue wiring, I guess. So from the power supply, these aren't very thick. They're 18 gauge, but since we're doing 24 volts, 18 gauge is pretty good. And we're going to use the prototype again. Functionality wise, there isn't anything different than what's on the current boards, but yeah, these are all fully 24 volt compatible, so you can feed 24 volt directly into the board, but always beware that in case you're running power directly to the LEDs, that the input voltage needs to be the same as the output voltage, or sorry, the input voltage needs to be the same as your LED voltage. This board does all kinds of DC conversions, but only for itself. It's very selfish. It tries to keep itself alive, but if you feed it 24 volts, the board will be fine. But if you then connect 5 volt LEDs behind it, those will fry for, you know, their life. So yeah, always be mindful that input voltage needs to is output voltage. I should replace these fuses. Yeah, maybe I should. Should I replace these fuses, or we're going to YOLO it? Nah, let's replace the fuses. They're in my box of fuses. There we go, box of fuses. 5 amp, no. 2 amp. 2 amp is good, I guess. Well, that's 48 watts. Do I have something else? What's this? No. I'd like some 3 amp fuses, but I don't have it. I'll put 5 amp fuses in it. So, how are we going to do this? We have our Dig-Quad, which has now been fused for 24 volts. But let's say that the beginning of a strip will do 5 amps. And then let's start with the scenario where we hook up everything together. So we've crossed or interconnected positive voltage, while in actuality you probably shouldn't do that, but let's test that. Let's see what happens. Right, and so then we need after the first strip, because we want to inject front and back on 5 volt strip, we're gonna do another injector here, and this is going to be a 10 amp one, and then we're going to take the 15 amp one, and we're going to do that here. And then we'll take, well, I don't know, another one of those, and we'll do that on the, well, you can't even see that, on the back end, basically. So, Dig-Quad, first injection line to the front, then second injection line to the middle, and then a third injection line to the middle here, and then a fourth injection line to the end, basically. Right? I hope that makes sense. And all those lines are going to be 24 volt, so we're not too worried about wire gauge and stuff like that. So let me just wire up the first part. Let's start with that, and then we'll just move on from there, right? And I think I'm just going to take the easy route, and that is hooking this one up directly without any wire in between. Is that cheating? I guess that's cheating. And one of the things that will be interesting today is if we can connect the positive lines together or not. Theory says we shouldn't really, because that way the DC converters will, in theory, start load sharing, and, well, we kind of don't want that because they're not designed to do that. So, yeah. Okay, and now the output wires, but I need some DuPont wires for that, or DuPont wires. I need some connection blocks for that to make it easy. Because let's do ground here and positive here, and let's take this one because we can connect it to the LED strip like so. We will connect power through the DC-DC converter. Oh, that's fine. And also minus. And then we'll just wire up the data connection directly. And we're only going to use one data connection for now. We might need a second one later, but we'll look at that. Okay, so what do we have? We have a Dig-Quad with positive 24 volts going. You guys really aren't paying attention, are you? I'm not either, so can't blame you. I actually wired up the board in reverse. Nothing will happen. It's been designed to be protected against that, but it's not good. Wow, I mean, when I have a headache, things don't work in my head, as is probably obvious by now. I wired up the negative wires to the positive terminals and vice versa. Oh. Anyway, it would have been protected. No worries. But yeah, Johnny, that's correct. We don't want one, in this case, DC-DC converter to backfeed into the other DC-DC converter. And even worse, maybe influence the regulator of the DC-DC converter, which often works with a feedback loop. If it would see pulsing from the other regulators, that might create some kind of feedback loop in the buck regulators themselves. But we're just going to try that today and see what happens. It could be that the resistance in the LED strip will be enough for it not to really be a problem. That doesn't mean it's good to do, but at least maybe it won't blow up when you do it, basically. Okay, let's look at this again. Now we have the right power wires going into the right terminal. So positive comes in here. This is also positive, good. It goes through the fuses. It comes out of here. It's still 24 volts. It goes into the input side, thank you, Philip, for the DC converter. This is a 5 amp block. And then it goes to the LED strip with a little connector in between. And we've just connected data directly because we don't really care about that right now, right? I don't know if I reflashed this this ESP32 or not. But let's just turn it on, see what happens. Okay. Well, we have light. That's good. Let's see if it got onto the wireless. I think so. So let's set this up for 900 LEDs. That's a bit too much for one data channel, but we're going to do it anyway. Okay, red. Blue is green. That's not good. So we go back to config. And we say if blue is green, so B and G should be reversed. So it should be this one. Okay, let's try it again. Red, blue, green. Okay, so if you ever have different LED strips, will use different ways of addressing the colors, basically. And yeah. So, okay, so this works. Let's see what it draws at white. That's about 23 watts. Okay, well, the reason I chose a 5 amp one here is because this is an edge connection, and the next connection we're going to do, so over here, will be a middle connection. So basically what we're going to do is very simple. We're going to, let me show you. We're just going to connect these together. I did it wrong. I shouldn't have put them on multiple interfaces. Minus, I want 900 LEDs on a single pin. Oh no, you shouldn't do that because you're going to get lag, blah, blah, blah. Yeah, I know. But we're going to do it anyway. Okay, there we go. So you can already tell probably that this right one is a lot dimmer than the left one. And that's because, well, the voltage drop is going to be insane right now. I'm going to turn it off, and then we're going to strip the injection wires you often get on the strip. And we're going to use that to inject power. Okay, so now we have a little splitter block so that we have plus from both strips and minus from both strips. And we can connect in our DC-DC converter. Yeah, true that running them on the spool is in theory a bad thing. Now, for digitally addressable LEDs, it's much less of an issue than for analog LEDs. Analog LEDs, I've literally melted spools before. But if we're just going to do some test patterns and stuff like that, or do it for like 10 or 30 seconds, digital LEDs will be okay. Analog LEDs, that's definitely a different case because those will run you very hot. But it's a good point to highlight. You shouldn't generally run your LEDs while it's still on the spool because they will not be able to radiate their heat and will die quicker, basically. And with analog LEDs, they can literally go up in smoke. Okay, so... Oh, okay, yeah. Got this to fit. It's good. Again, I'm not going to bother with wires in between because we looked at the wires in between last time. So we kind of know what the influence of the wires is. And even if we're sending out 24 volts from the Dig-Quad in this case, if it's like 16 or 18 volts once it reaches this converter, it's still fine because it only needs to convert to 5 volts. So that's fine. So it does seem like this connection is loose. Okay, better. Because you can definitely see the difference in color there. But it does seem like they're kind of balancing. Let's go to full power for a little bit. Not too long. So full power, this is drawing about 5 amps. Okay, sure. And this one is doing 1.7, 1.8. Okay, but that's normal because, as I said, this is an edge connection and this is a middle connection. And the middle connection will always have more drawn, especially since we connected the power wires of both through this splitter block. We can also look at the voltage, but it should be pretty good now. So, let's see here. Right, because we're measuring basically at the output of a DC-DC converter. So we're measuring a perfect 5.17 volts. And I can't easily measure on this block because I can't stick the pins in here. But this one is also going to be giving off 5 volts. So, yeah. So far it's not that big of an issue. But let's say... so... The reason that it's expected that the middle is going to draw more is because basically power can travel both ways. So it can travel into this strip, but it can also travel into this strip. And if the strip is the limiting factor in how much power it can draw because of voltage drop, well, it has twice as much of copper close to it than an edge connection will. Does that make sense? So power flows both ways, and thus it has twice the amount of copper to spread, and thus it can basically draw double if voltage drop is the same over the amount of copper, because we have double the amount of copper next to our connection points. Cool. Okay. So far, this seems to be working fine, but how do we simulate if something goes wrong? Okay, let's put it full power, right? We're drawing 44 watts from the socket. And now let's disconnect this one. We're now drawing 26 watts from the socket. And now let's disconnect this one. We're now drawing 21 watts from the socket. That means that now everything is being supplied by this DC-DC converter. And that is in part the reason why you don't want a setup like this. Because if this DC-DC converter wouldn't have a limit, it could potentially be being overdrawn, basically. Because now it's delivering almost 3 amps instead of the 1 point something that it did before. Now, it's a 5 amp converter, so that's no problem. So maybe you can connect everything together as long as you make sure that each individual converter can survive if one of the others fails. We can think about that. Is that a decent conclusion? So just connecting ground already helps a lot. And then connecting the extra 5 volt really brightens them up. Oh wait, I guess if I disconnect this one, so I disconnected the middle positive, we can still measure voltage. Yeah. It's at 3.2 volts because it's have to go into the strip. But if I now also disconnect negative, yeah, now it's at 2.6 volts. So we're injecting 5 volt here, but then because it has to travel all the way through the strip, even running a little pattern and stuff like that, it's down to 2.7 volts. I'm amazed these still work, actually. But yeah, so that is the issue with having multiple converters on the same positive rail. If one of them fails and the other one then tries to compensate for that, but it can't handle it, or the cables in between can't handle it, or something like that, that can potentially cause an issue that you need to watch out for. But adding wires would make it even more complex to do it just on the table. Right, so to resume, we have an initial connection, initial edge connection going to a 5 amp block, which is then fed into this LED strip here. 300 LEDs later, ws2812b. We have a middle connection, which is being fed through this 10 amp block, which is then feeding both these strips with the power injection wires, and it's connected, so everything there is connected. Then it goes to another 300 LEDs. Then we have another 10 amp middle injection. We also have the LED strip connected, so all the positives and all the negatives, they're all connected. And we're not using fuses on anything on this side, which is never a good plan. But we do have fuses here. So if something would very roughly overdraw something, the fuses here would still pop. So that's good. We don't have an edge connection yet. We can do that later because per 300 LEDs you want to inject front and end with another 5 amp converter, but we don't have that one yet. Okay, let's see if this works. Oh, you think 5 amp for each injector would be fine how I have it. That depends. 300 ws2812b LEDs can use up to 13 amps. So a middle injector will do, well, it'll go left and right, so it could easily feed like 200 on the left and 200 on the right. And then even 10 amps officially wouldn't be enough if you do full brightness white. Now, generally you don't do that, but let's say currently this seems to still be working fine. We can quickly do that. So if I go here, I set it to solid. Let's set it to white. That's my multimeter. We're now drawing 85 watts, but it's only at 50%. And now we're drawing 133 watts. Now, I'm not going to do that very long. If we take the calculator and we calculate 133 divided by 24, that means we're asking 5.5 amps from the power supplies, or the wires that are over here, basically. So wires from here to the blocks are only needing to transport 5.5 amps in total. But if we take that 133 and we divide it by 5, that means we're drawing 26 watts. Or No, that means we're drawing 26 amps. And, well, set to white, these do become hot. But 26 amps is 10 plus 10 plus 5. So, no, you do want 10 amp converters in the middle, basically. That's what I'm saying. No, so I don't agree, Blake and Patrick, that 5 amp would be fine because, well, 133 watts incoming, sure, there's some conversion loss somewhere, but that's 26 amps at 5 volt. So if these would have been 5 amp converters, that wouldn't have worked, or they would have been heavily overdrawn. And especially if one would fail, the other one would be even more overdrawn. So I'd always caution on the high side, getting 1 or 2 models above what you think you'll need, versus what you think you could get away with. So if we look at QuinLED.info and we go to the addressable LED section again, and we look at my digital LED power usage sheet, and we go to the 5 volt sheet, we see that ws2812b at 100% white uses 65 watts. The sheets are all in watts because you can then easily compare between 5 volt, 12 volt, and 24 volt LED strips. So watts is always the same, and then you can just divide it by the voltage you're running to find the amps. And 65 divided by 5 is 13. So one of these rolls, if properly injected, and all my tests at 5 volt are done with a front, middle, and end connection, will draw up to 65 watts, or amps, well, 65 watt or 13 amps full white. Now, if you look at the other patterns like police all, or loading, or even rainbow, or a single color, we see it's only drawing 25 watts. So that's a whole lot less. But maybe if something software wise goes wrong and all the LEDs suddenly jump to white, you do want to be slightly prepared for that scenario. Either by fusing pretty low and then popping a fuse, or just making sure the setup can handle it. Okay, let's hook this up. Turn it on. Okay. This looks okay. Well, let's go to full white, see if that makes a difference in power draw. Oh wow, it does. We're now at 150 watts drawn from the socket. And let's take a look at all the converters real quick. Oh. This one is doing about 2 amps. This one is doing about 8 amps, so it's doing slightly less because the other converter is now closer, providing a higher voltage. So part of the LEDs are getting their power from there, and part of the LEDs are getting the power from here. This one is now doing about 9 amps, and this one is doing about 3.4 amps. And in total, we're looking at 5.19. Okay, let's say this middle converter dies, and let's keep the amp meter on the other one. Right, so we have the first middle converter, that's this one, and then we have the second middle converter, that's this one, that's because those are the 10 amp ones, and then we have the last end converter. But let's say this one dies, right, and it dies by disconnecting the wire, or wires. Okay, but we see the LED strip dim slightly because now there's more voltage drop going over the LED strip, and that'll in turn automatically also limit power. So we don't see a drastic amount of extra draw here. So let's connect that back. So we're now at about 3 amps. Okay, and we're now at 1.74. Okay, so we do see extra draw, but the extra draw isn't going to be unlimited because of the tiny amounts of copper on the LED strip, which will in turn limit power, basically. Yeah, same is true here. So when I disconnect the middle injector that's close to here, you see that it starts using more power, but the amount of more power that it can actually use is limited by the voltage drop going over the strip. If this was a wire in between there, we might be overloading that wire, but since this is an LED strip which suffers from voltage drop anyway, the amount of extra current that will get drawn is pretty limited. Yeah, that's right, Shoddy. I'd also go for the 10 amp ones, even on the edge connections, just to be sure. And then maybe on the middle ones I'd go 15 amps, just so you know you have the headroom that if something does fail, you're still not overdrawing it. So let's go to white, and let's go to maximum brightness. Yeah, we're still drawing 151 watts, so basically nothing changed. And let's measure the amps on this middle injection here. 8.49. So even though we have the 15 amp right here, and well, we can measure this one too, and a 10 amp on the edge injection, so 15 amp on the middle injection, we're seeing the same numbers. So my initial thoughts about using a 10 amp in the middle and a 5 amp on the outsides were pretty spot on. I personally, if I'd be building this for real life, I'd put a 10 amp on an edge connection and maybe use one of these cheaper plastic ones. That's fine. And then I'd put a 15 amp one on the middle connection. And if, for instance, if you're using a higher draw chip, like maybe sk6812, because you also want to do some warm white and stuff like that, then certainly use a 15 amp for a middle injection.